different. And so what happens is, I feel like we learn the polar stuff, and then like a big chunk of the parametric stuff just like falls out of all the students' brains. Okay, so you've got to delineate between the two and make sure you retain all this stuff about parametric functions, and then differentiate that between that and polar, the stuff that we're about to do this week. Okay, so don't, on the final exam, don't, make sure you study and know parametric, all the aspects of parametric functions and the calculus of them, and can differentiate between that and polar functions and polar calculus. Okay, so here is, they want us to find dy dx, and we know that's just dy dt over dx dt. So dy dt is going to be, from here it's going to be 2 minus 1 over t, and then we're going to take that all over dx dt, and so that's going to be a 4 plus 1 over t. Now to do the second derivative, remember what we said the second derivative was? The second derivative is the derivative of the first derivative, what we just did, with respect to t, over the derivative of x with respect to t. Okay, so we're going to have to do this with respect to t. Now there's something we need to do before we start doing the we're going to have to do the quotient rule on this. But it's going to be a whole lot easier if we start by multiplying the top and bottom by t and getting rid of these fractions. So I'm going to multiply by 1 in the form of t over t, and that's going to make things a lot nicer. We're going to get 2t minus 1 over 4t plus 1. And now the quotient rule for this, so doing the derivative of that, dy dx, with respect to t, that's going to be a lot friendlier. So the quotient rule is going to be low d high minus high d low over low squared. And that's all over dx dt, which is not 4t plus 1, all right, because that's dx dt times t. So we need to go back to this 4 plus 1 over t. And so what we want to do is we can just leave it like this, and we just write it in a line like this with parentheses, but then use preview to make sure that when we use preview, we get this expression. So we don't, it's much easier to like just try to get this typed in and get it right with the preview than doing any simplification here. You might simplify this numerator of the numerator. That's okay. That'd probably be okay. So 8t plus 2 minus 4t plus 4, and just simplify that, or just leave it like it is. But that's that one. So that is, what is that giving us? The rate of change of the rate of change with respect to x, but in terms of t, in terms of the value of t. Questions on this one? Yeah? Because this is, if you kind of look at how the units work out here, so this is the second, this is taking the derivative of dy dx, but with respect to t. So that's not going to give us the second derivative of y with respect to x. These needs to go away. I need to get rid of these dt's so that I have dy dx dx. That's this. Does that make sense? So without doing that, this expression is not the same as our standard second derivative there. Does that help? Yes, sir?
So I was a little confused. So basically that expression of dy over dx over dt is basically kind of equivalent to d squared y.
Yeah, we proved that in class. We showed that in class.
Oh, okay.
Yeah, in class last time, or yeah, before the test, we showed that this was equal to this. So that's from your notes. Other questions on this one? Okay. How about 5? Okay. So we need to find, we've got this curve and the line 17/4, and we need to find the area bounded by that region. So what happens is if you graph this, you get a graph like, not like that. Let's try that again. Better? Okay, and then 17/4 is up here like this. And then this is our parametric equation there. So what we need to do is we need to find these t values right here. The values of t that give us those 2 points. So whatever those are, t1 and t2. Yeah?
In the future, when graphing the parametric, will we just have to do that manually with our, like, just find order pairs and just graph it out to visualize it better?
Yeah, and your TI will do that also. If you put your TI in parametric mode, it can take pairs of xt, yt. So your graphing calculator will do that as well. So yeah, one of the two. Okay, and so if we want the area between those two like that, then we're going to, so it's really, we think about it the way we do before. It's going to be the integral of this function minus the integral of this one, or like if we do it, remember we did typical strips, right? A typical strip. And what's the area of that typical strip? It's going to be, the height of it is y2 minus y1, and then the width of it is delta x. And we're going to add all those up from t1 across to t2. But for polar coordinates, we know that it's so y dx, or I'm sorry, in parametric coordinates, it's going to be, so if this is, say, g of x, g of t, and x is f of t, then it's going to be y is f of t, and then, y is g of t, and then dx is going to be f prime of t dt, and we showed that in class also. That this is how we're going to find areas with parametric, but it's totally based on the same vertical rectangles, the height of y and width of x that we did before. We're just transferring it directly into t, so there's our y and there's our dx. So now it's just it's the difference of y's, right? So it's the difference of y's, so this is going to be upper y minus lower y. Upper y is 17/4. It's going to be 17/4 minus lower y, which is our t plus 1 over t. And then times f prime of t dt. So f prime of t is going to be 1. That turns out to be plus 1 over t squared dt. So there's our y2 minus y1 times dx, which our dx is going to be dt, which is 1 plus 1 over t squared. That's the derivative of that, dt. So all that's left to do is get the t1 and the t2, and it's going to be that. Is there a question? Yeah, tell me. Ask me.
I understand that you have 1 plus t squared, but how do you make 17/4 go in with g of t?
Because it's a typical slice, right? So we're doing it, a typical slice is, so it's like height times width, right? And the height is this y coordinate minus this one. Highest y minus lower y is the height of that typical strip right there. What is the higher y? It's just 17/4. And then what is the lower y? Well, it's according to this function, which we have in t plus 1 over t. Oh, so actually this is, notice the parentheses there. It's 17/4 minus the function t plus 1 over t. Did that help? Do you follow that? Yeah? Okay. But it goes back to what we did at the beginning of the semester. Typical slice right there, that red typical slice is height times width. Height is upper y minus lower y. Upper y is 17/4, lower y is that function right there. Okay, so and then getting the values of t, you can just, if you want to do algebraically, you do 17/4. We're looking for values of t such that the y's are equal for these, right? So that the y of this is 17/4. So you can do 17/4 equals t plus 1 over t. Multiply both sides by t and you get a quadratic. And those will be your two values of t. Will be your t1 and your t2. So solve to get t's that are the boundaries. Yes, sir.
I remember when we were doing the example in class, like the parametric function like overlapped with itself.
Right.
So there was part of it that was like positive, part of that was going to be
Right.
like
We don't have to deal with that here because everything's good. Everything's just clearly an upper function and a lower function. It doesn't curve around on itself. Yeah.
But is that only going to occur when the parametric function overlaps itself for the most part?
Yeah, you're gonna follow exactly what we did before as when it wasn't parametric. So in this case here, you're just gonna have all vertical slices, no curveballs, right? No, there's nothing going on here. But yeah, if it's a non-function like that, not a function of x, that's where you get that kind of weird thing happening. But this is much easier. This is much more straightforward. Other questions on this one? Okay, so that's the integral setup, and then this is how you find those. This is one way to find those values of those t values for your limits of integration. Okay, let's do one more here. Oh, I don't want that. I want this. Okay, so the highest point is going to be when what? The highest point is a horizontal tangent. And so what is that? What derivative is going to help us get that? dy dt is 0. And now dy dt, that's product rule. Product rule. So dy dt is going to be, say, first times the derivative of the second plus derivative of the first times the second. And we want that to be 0. So there's our product rule for dy dt. And so e to the minus t is never 0. Okay, this e to the minus t, exponential function like that, you can never get that to be 0. And so we can just, in fact, we can just kind of factor it out and don't have to worry about it because it can never be 0. So e to the minus t will be times negative 2t plus 2. And so our t value will be 1. And that the t value of 1 gives us a dy dt of 0. And so then the highest point is what you get when you plug 1 in here. So 9e and 2e. So when t equals 1, x is 9e, and when t equals 1, y is 2e. So we do the same thing for the leftmost point. We'll have product rule. It will be dx dt equals 0, right? Because it'll be a vertical tangent. Probably. 2 over e? Yeah, thank you. 2 over e. Thank you. Yep, so it'd be 2e to the minus 1. Thank you. 2e to the minus 1. So it'd be 9e and 2 over e. So then the horizontal, okay, so asymptotes. So asymptotes would be, how do we get asymptotes? We get asymptotes when t gets really, really big positive or really, really big negative. Okay? So when t gets really large, what happens to x? X just gets really, really big, so that's not, so we know it's going to go way out to the right, and then what's y going to do? Y is going to go to 0, right? So this, the limit as t gets really big, y will go to 0. So that's telling us that for very large values of t, we're going to go way out to the right, and we're going to get closer and closer to 0. That's horizontal asymptote. And then we try t getting very, very large negative. And when t is very large negative, this now will get very large. Y will get really big, and x will go to 0. Right? Because the limit, so as this will get very large negative, but e to a large negative will go to 0, or get e to a negative large number will get small much, much faster than t will get large. Okay? So this will also be 0. That's extra credit, because we didn't talk about that. Okay, so again, as we start this polar stuff, it kind of feels the same, but it's different, and so don't erase the big ideas from and these techniques that you learned in these problems here for this homework.
So leftmost, you're just solving for x.
Say it again?
Leftmost, you do the derivative of x.
Yeah, leftmost point is going to look like this. So what's happening there at the leftmost point? Vertical. Yep, so dx dt. So for a small change in t, dx is 0. Okay, other questions? Okay, so let's go on to polar. This is the last tonight and Wednesday night, polar coordinates. It's the last thing we do. Okay, so polar coordinates. So our graphs so far, even in parametric, so your whole math career and even parametric functions are based on an x-coordinate, which is how far left or right, right? X-coordinate, how far left or right, and a y-coordinate, how far up or down. So, you know, if the point is 3, -1, you all know that you march over 3 to the right, and you march down 1, and you get this point here, 3, -1. And that's the land that you've lived in for the last 10 years of your math career, okay? So polar coordinates is a different way to locate places on the plane. It's a totally different way of doing it. You don't use a left and right and up and down approach anymore, an x and y approach, but instead it's based upon distance from the pole. The pole is the origin, okay? So it's like you're looking down on the Earth. It's like the North Pole, right? Looking down, or the South Pole, looking down on the Earth. The pole is the center, the origin, and it's the two things that you look at to locate points are how far you are from the pole. So like these radial lines are helpful for measuring how far out, right, along these radial lines, how far. And then the other coordinate that you use is theta, which is your standard trig angle, which is the angle swept counterclockwise from the x-axis. Okay? So let's take a look at this here. So polar curves have the form r as a function of theta. So so you have some expression of theta, and as theta increases from the positive x-axis this way, as you rotate around, you have a corresponding distance from the origin for every theta. So for every theta that you have a distance from the origin. So let's see what that looks like. Here's an example. So notice we're rotating around here. So like for instance right here, right now we're looking at this angle, the input of the function is this angle measure right here. That's our theta. Terminal side is the positive x-axis, and right now the initial side is the positive x-axis. Here's our terminal side right now. That's theta. And then for the function designates for every theta a distance from the pole. So right now for this theta, it's saying that the distance is like almost 3.5. Do you see that? This is 1, 2, 3.5. So this distance right here is r. So this point right here, so I'll call this theta 1 and r1. So this point right here has coordinates r1, theta 1. Now ordered pairs are listed backwards from what we're used to, right? Because we're used to x comma y, which is like input comma output. But when you do ordered pairs in polar, you do r comma theta, but theta is the input, so it's kind of like you're doing output comma input. So just be aware of that your ordered pairs are listed as r comma theta when theta is thought of as the input and r is the output. Okay, so the function designates a distance from the pole, or r, for every given theta. And so if you have a function like this one, as theta increases, it sweeps out points. So let's, so here's another one. So let's practice here. So this is, our theta is now, this is theta right here. And now r is like 2. So this is not negative, right? Because it's positive distance from the pole at the angle. So the angle, here's the terminal side of the angle. And along the terminal side of the angle, r is always positive. So this is about positive 2.8. You see that? So this is about positive. So this is theta 2 now. And r2 gives us this point right here, where r2 is about 2.8. And what is theta here? I'm breaking this up. 6. 15 degrees, so this is 150 degrees. So theta 2 is 150 degrees. R2 is about 2.8, and it gives us that point right there, which has the ordered pair R2, comma, theta 2. Question?
Instead of theta 2 and you're actually plotting the points, would you say that's 5 pi over 6? Or you said it's 150 degrees.
Is it 150 degrees? Let's see.
Well, just
yeah. So if you're theta could be in degrees or radians. It doesn't. There's no whatever you're measuring your angle in. So I just called. So this is 1, 2, 3. Yeah, I'm dividing up 60 into 6, which is 15 each, right? Yeah. So that's 30. So that's 150. Yeah. So it's also 5 pi over 6. If you're doing radians, it would be 5 pi over 6. So all this blue curve that's being traced out is all these coordinate pairs according to this function f of theta and a corresponding distance away from the pole. So if I keep showing you the graph, this particular one makes a pretty butterfly. Isn't that sweet? My daughter would love it. Okay. So this particular function is e to the sine theta minus 2 cosine 4 theta. So it's more advanced than what we'll do, but I just thought it was a cool example to start with. So again, it's the idea of a function. Every given theta gives you a corresponding value in this expression, which is then the corresponding distance from the pole. And then as you trace out all those points, you get this design here. Okay, so that's a little introduction there. So let's talk about, let's make it start a little bit easier here. So let's look at the point. So where would 3 comma pi over 4 be? Could you imagine where 3 comma pi over 4 would be? First quadrant. So we're going to go to pi over 4. That's the angle. Distance of 3 from the pole. So it's going to be this. Oh, here you go. Pass to your right as well. Pass to your right. Pass to your left. Okay, so what is the point 3 comma pi over 4? Again, this is not, it's not 3 to the right and pi over 4 up. It's a totally different way of locating points in the plane now. It's a distance of 3 away from the pole, the origin, at an angle of pi over 4. So I'm showing, can you see I'm showing, highlighting that angle right here. And so now we're going to go a distance of 3 away. 1, 2, 3. Do you have the same, is it also 1, 2, 3, 4, 5? Is it split up the same way?
Yeah.
Great, awesome. So that's that point right there, 3 comma pi over 4. So now this point right here. So the thing about polar coordinates, unlike Cartesian coordinates, x and y coordinates, is given a point, there are actually many ways to represent coordinates for that point. So the obvious way for this one would be an angle of, what angle would we have to get us there in the third quadrant? That'd be 5 pi over 4. So we could do 5 pi over 4. And then what's r? So there's 5 pi over 4 and 1, right? So it would be the point 1 comma 5 pi over 4 would kind of be the most obvious way to do this. Okay, but let's go back and let me show you here at, going back to pointing, right? So now I'm pointing the black, so black is pointing in the direction of pi over 4. So if at pi over 4, all along here is positive r going away, getting greater, going away from the pole, then what would this be down here then? So this would be negative values of r for an r of pi over 4. So therefore, we could also write this point how? R would be negative 1 and pi over 4. So I'm showing that in red. So I'm showing the red side of the angle would be negative values of r because it's pointing exactly the opposite direction in where the terminal side of the angle points. See that? So the terminal side of the angle is pointing up to the right at pi over 4. Therefore, negative values of r would be pointing exactly the opposite direction down. So this would be, for the angle of pi over 4, this would be negative 1, negative 2, negative 3, negative 4, negative 5. But for an angle of 5 pi over 4, that would be this in the positive direction for a distance of 1. So it's the same point. You see that? Yeah, the whole point is that they're all the same point. They're all the same point. Okay? There's still another way to do this. What would be another way to get to this point?
1, 3, 5, 4.
Okay, so the angle, what if we swept, instead of sweeping counterclockwise, we swept clockwise? Right? So we could sweep clockwise like this. What angle is that? Negative 3 pi over 4. And then would R be positive or negative to get that point? Positive, because at negative 3 pi over 4, the terminal side points down into the third quadrant. So the ordered pair would be positive 1 and negative 3 pi over 4. Okay, we could do 5 pi over 4 plus another 2 pi, whatever that is. 13 pi over 4. Okay, so we could do 13 pi over 4, and that would take us to the same positive, or the same terminal ray as 5 pi over 4. So 1 comma 13 pi over 4 would also give us that same point. So there's really, given a point, there's really an infinite number of ways to get it, with positive angles, with negative angles, with positive values of R, with negative values of R. Okay, so one last way here. If we did a negative angle all the way into the first quadrant, what negative angle would that be? Negative 7 pi over 4. So I could sweep clockwise to negative 7 pi over 4, and then my R value would be negative 1. Uh-oh. Forgot my water. And my Kleenex. Okay, so it seems like slightly, or it seems attainable. It's not too hard. But when we start sketching these functions and R is changing between positive and negative as the angle turns, you have to have this idea down pat because it gets confusing quickly. Because as theta goes around, R is going to change from positive values to negative values as we try to sketch these curves. So you have to really know where you are in the plane for any given angle. Okay, so now going back to that point, let's just go back to this first point here. And this was 3 pi over 4. What are the x and y coordinates of that point? So now if we wanted that same point, but expressed as x and y, because this is now expressed as r theta. So how are we going to get, so what would that be? So we're thinking about that distance would be our y coordinate, and that distance would be our x coordinate. So we need our trig, right? Because it's the same angle from trigonometry, swept counterclockwise from the positive x-axis, right? So that follows right along with our so that distance right there is 3, and this is our theta, 5 over 4. So who remembers the trig? So what distance is x?
3 cosine pi over 4.
Right. It'd be 3 cosine pi over 4. And y would be 3 sine. Which would be 3 radical 2 over 2. Both of them would be 3 radical 2 over 2 in this case. Cosine of pi over 4 equals sine of pi over 4 equals radical 2 over 2. So the xy coordinates at this point would be 3 radical 2 over 2, 3 radical 2 over 2, Same point, just using different coordinate system to get to that same place in the plane. So let's generalize this here. So if we have any angle theta and distance r, what are the x and y coordinates? So for any, so let's just put the point out here, just any point here. This for distance r and an angle theta. Coordinates are r, theta, and polar, and what would they be? Right, so as xy coordinates, it would be r cosine theta, r sine theta. And that's going to be important because in a lot of these problems we'll be converting back and forth. We'll have the polar, we'll have it in polar, and we'll want xy coordinates, or we'll have it in x and y, and we'll want it shifted to polar. So we have it in polar, we want it in x and y. That's this right here. So x equals r cosine theta, y equals r sine theta. Now the opposite is we have something, an equation or a point in terms of x and y, and we want it in r and theta. So if we knew the xy coordinates of this point, what would r be? How would we find r given the x and y coordinates of that point? Yeah, Pythagorean theorem. What does r equal? You should all be thinking that, right? Radical x squared plus y squared. It's just the length of the hypotenuse given the length of the two legs. Okay, theta then? Okay, so the tangent of theta is opposite over adjacent. And so then theta is the inverse tangent of y over x. But if you remember about your inverse trig functions, that's going to always be an angle between negative pi over 2 and pi over 2. So if you do an inverse tangent of y over x, you're always going to get an angle between negative pi over 2 and pi over 2. So if your angle is something different than that, like in the second or third quadrant, then you're going to have to adjust, okay? Because it's going to give you the symmetric or equivalent angle in the fourth or first quadrant from negative pi over 2 to pi over 2. So just be aware of that. But given r and theta, this is how you would get the corresponding x and y. Given x and y, this is how you would work towards the corresponding r and theta. Okay, and then these relationships hold no matter what theta is, no matter what r is. You just get a different right triangle, but all those same relationships hold for a different theta and a different r. Okay, so you need a little practice here. So I want you to plot each point and find rectangular coordinates. Sometimes thinking provides a lot easier solution than blindly using formulas. Okay, so think before just cranking out some formula without using your brain. Okay, so Okay, again, think about what you're doing before just running to formulas mindlessly, okay? Okay, and I'll take a 10. Okay, what is 1 pi? So we're going to go pi takes us to the negative x-axis. We're going to go distance of 1. We're going to plot that point, and then we're just going to write down the xy coordinates, right? Which is? Negative 1, 0. No math to do, right? No math to do. Does that make sense? That's the point, negative 1, 0 in the xy plane. You don't have to do the formulas. That's what I was getting at. Okay? Negative 2 pi over 3. What quadrant is negative 2 pi over 3 in? Third. We're gonna sweep this way. 2 pi over 3 is going to take us to this line right here. This line right here is 2 pi over 3. And we're going to go positive 2. First or third quadrant? Third. Here it is. There's that point for part B. XY coordinates. It's actually going to, it's going to be 2 cosine of this, and then 2 sine of this. 2 cosine of this is actually going to be negative 1, because cosine of this is negative 1/2 times 2 is negative 1, and then sine of this is negative radical 3 over 2 times 2, negative radical 3. So as xy coordinates, it is negative 1, negative radical 3. If you remember your unit circle. So that's for B, xy coordinates. Okay, 3 pi over 4, negative 3. What quadrant is that going to be in? 1, 2, 3, or 4? 3 pi over 4 is halfway through the second quadrant. And then negative 3 will put us in the fourth quadrant. And we'll go 3. So it'll be 1, 2, right here. That's C. That's negative 3, 3 pi over 4. Questions on locating the points? And then that will be, this will be 3 pi over 4. Sine and cosine will be radical 2 over 2 and negative radical 2 over 2, and then times 3. So as xy coordinates, you'll be positive 3 radical 2 over 2, and then negative 3 radical 2 over 2. Those are the xy coordinates for that point. Okay, now this one, which we originally said was 2 negative 2 pi over 3, we want to write that 3 different ways in polar coordinates. 3 more ways in polar coordinates. Suggestion, one way to do that. What's that? Minus 2 and pi over 3. Does it work? Yes. Yep. Pi over 3 brings you here. Minus 2 then brings you down here. Another one. Yeah. Go ahead. 2 and 4 pi over 3. 4 pi over 3 takes you all the way here into the third quadrant to that terminal side, and then positive 2. Good. And we got another one. What's that?
2 10 pi over 3.
2 and 10 pi over 3. So let's see. Is that right? 4 pi over 3, another 6 pi over 3. That's right. 2 and 10 pi over 3 works. One more suggestion.
Negative 2 and 7 pi.
Negative 5 pi over 3. That's the one I was thinking of. Negative 5 pi over 3 puts you here, and then negative 2. So negative 2, negative 5 pi over 3. But there's, just keep adding 2 pi to any of those angles, and you have that same point. Okay, questions on locating points and then switching between polar and XY coordinates. Okay, so now we want to get into some, yeah, please.
So when you mentioned like just add like 2 pi over 3, then when you ask us for like 3 other ways of color coordinates, do we just have like
It's more about an idea than this is going to be a test question, right? So just understand the idea, and then you can answer answer many test questions.
Okay.
Yeah. Okay. So let's look at this function right here. So if we said r equals 2 sine theta, that is r as a function of theta. So this will graph as a curve in the polar plane. So rather than just picking a bunch of angles and getting the corresponding r's and plotting a bunch of points, we want to take a more mathematical approach to this. And what we want to do is we want to first graph this. First, we want to graph this in Cartesian coordinates where we're going to put theta on the horizontal axis and r on the vertical axis, and then we're going to use that graph to help us sketch the polar graph. Okay, so what do we have? We have to know our our transformations of sine and cosine graphs. Okay, many of you will have to brush up. That's been my experience. That was a while ago, and that's not an easy thing. And so hopefully this first one, 2 sine theta, we could sketch. What's the period of sine theta? How much theta does it take for this thing to repeat? 2 pi. Okay, so we'll put 2 pi right there. Maybe we'll sketch out 2 periods, okay? 2 cycles. Okay, so that's just that knowledge you have to have. Sine and cosine by themselves have a period of 2 pi, meaning it takes a full rotation for that coordinate to repeat again, right? And then for just sine theta, what's its maximum and minimum? So just sine theta. 1 and negative 1, right? Sine theta is going to have a max of 1 at the top of the circle, and then to 0 over here, and then negative 1, and then back to 0. And at theta equals 0, what is the sign? Is it the midline, or the max? It's 0, right? Because for an angle of 0, our sine is 0. Okay, and then it's going to stay between. So this particular graph will stay between what and what? 2 and negative 2, because sine stays between 1 and negative 1. The biggest sine gets us 1, so then the biggest 2 sine gets us 2. The smallest sine gets us negative 1, so its smallest is negative 2. So now we're going to sketch. And when we sketch a period, we break it up into 4. 4 equal, right? Kind of thinking about going around the circle. Each quadrant gives us a kind of a standard piece of the. And you told me it starts at 0, and in the first quarter it goes up, right? Goes up to 1, or in this case, 2. And then, as theta goes from pi over 2 to pi, goes back to 0. Good. And then pi to 3 pi over 2. We'll go down to negative 2. So this is an easy one. So these, we're going to have some practice sketching some harder ones. And then if we go around from 2 pi to 4 pi, it just repeats. Does the same thing again. So there's 2 cycles of 2 sine theta. Here's 2. Here's negative 2. Now we're going to use that graph now to help us sketch what this function will look like in the polar plane. Okay? So we're using covariation. We're saying as theta goes from a starting angle to a finishing angle, this distance from the pole is going to go from something to something, and we're going to put that stuff together. So let's go from so we're going to look at this first quarter period here. As r goes from 0 to pi over 2, as theta goes from 0 to pi over 2, what does r do? Increases from what to what? 0 to 2. 0 to 2. So you might, if you're going to sketch this graph, you might change your, I would change your, the axes to, instead of 2, 4, do 1, 2 on all, so in all directions, right? Instead of 2, 4, you're going to do 1, 2. So you're not trying to draw this, it'll be too small in the middle. So just, we're like magnify the axes, okay? So it's, or zoom in so that instead of 2, 4 in all axes, it says 1, 2. Okay. Maybe I'll do that too. Let's see. Okay, so as we go from, what did I say? As we go from 0 to pi over 2, r is going to do what according to our graph? So we're looking at this. As we go from 0 to pi over 2, so looking at this right here. This graph tells us that r does what? It starts at 0 and going to go to 2. So we know we're going to have the point, what? 0, 0 at an angle of 0. It's going to be a distance of 0, but then we're going to rotate, and then when we get to pi over 2, we're going to have the point, what? Pi over 2, comma 2, which we know is up here. But what happens in between is the tricky part. So we think about every time we increase the angle, what happens to r? It increases, right? So so here's that first segment. I'll throw it out here. I'm just kind of guessing, right? As I'm thinking about as theta increases, r is increasing, getting farther. So now we are halfway through. Should be farther than halfway up, so maybe like this. So do you see what's happening? So as I'm increasing the angle theta, r is increasing. So here it's something like a half, almost 1. What is it, like 1.2 now? And then like this. So do you see r increasing, getting further from the pole as theta increases? That's what that graph tells us. That's what that graph tells us. As r increases, as theta increases, as we rotate around, r increases from 0 to 2. So our points are getting further away until we reach 2. Can you see that? So you can think about that happening rather than point by point, continuously happening. So as we're rotating around, r is increasing as we rotate theta. Something like that. So this is the idea of covariation, how two quantities are changing together, and we're getting that information from this right here. As theta increases, r increases from 0 to 2. So now what happens in the second quadrant? So as theta keeps increasing from pi over 2 to pi, meaning we're going to rotate through the second quadrant, what happens to r? It decreases back to 0. And look, in a symmetric way, right? In a symmetric way. Like, and now it's going to go back down. So we think about the angle increasing through the second quadrant like this. Boom, 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 boom. And r is now going to decrease back to 0. So do you see that? It will kind of be symmetric here. So you can kind of just sketch some points. Let's make something like that. Okay, now, third quadrant. We're going to go from pi to 3 pi over 2. So as we go from pi to 3 pi over 2, what does r do? It goes from what to what? 0 to negative 2. Oh no. So now, look, all those r values are negative. So we're going to rotate through the third quadrant here, but we're going to rotate through the third quadrant, but all the r values are going to be negative to negative 2. What is that going to give us? It's going to overlay. It's just going to replot those same points that we plotted in the first quadrant. Do you see that? As we sweep through this third quadrant, now it's going to be the red side, right? All the r's are going to be negative from 0 to negative 2, and it's just going to trace on itself again. So I don't have to redo it. I've already done it. And then the fourth quadrant, r is going to go from what to what? Now we're looking here at the graph here. From 3 pi over 2 to 2 pi, r is going to go from what to what? Negative 2 to 0. And what's that going to do? It's going to retrace what we already did in the second quadrant, right? So here's 3 pi over 2, negative 2 up here. And as the angle sweeps through the fourth quadrant, r is going to it's going to actually go from negative 2 to 0. So just like that third part of the graph mimics the first part, this fourth part is going to mimic and give the same set of points as the second part. And then it's from 2 pi, it's going to start all over again and just keep rewriting this. Okay, so all we need in this particular graph is pi to get the full set of points. After pi, it just keeps repeating, whether the r's are negative or then back positive again, or r's are negative or positive. Okay, so that was an easy one. That was an easy one. But let's take a look at what we got. Okay, so we've never seen a polar function before, so we don't really know what we have here. So can we change it into x and y? If we can change this thing into x and y, then it might tell us what we have. We might recognize what we have. Okay? So, what is r in terms of x and y? X squared plus y squared, is that right? Square root, right? Square root. And what's 2 sine theta? What is that in terms of x and y? Well, who knows, right? So we need to make this easy on ourselves here. So what can I do to 2 sine theta to get something real easy in terms of changing it into x and y? If I had something else, what would be really helpful? Instead of just 2 sine theta, if it was 2r sine theta, because then what would it be? It would be 2, oh, how quickly they forget. X equals r cosine theta, remember? Y equals r sine theta. So look, I have 2 sine theta. What if I had 2r sine theta? Then what would that be? 2y. But if I multiply the right by r, what about the left? Got to multiply the left by r. But that's actually kind of good. What is r squared? So r squared is, by the Pythagorean theorem, x squared plus y squared. And then 2r sine theta is? Okay, this is looking nice, right? So this is looking nice now. We don't have to do any crazy stuff with arctangents or solving for angles. So what do we have here? X squared plus y squared equals 2y. Anyone recognize what we have? So we need to get this into our circle form. So we're going to subtract the 2y. And what we need to do on this y now is complete the square. We need to complete the square. X squared is fine by itself, but what completes the square? We're going to take half of the linear coefficient and square it. So our linear coefficient is -2. We take half of that and square it and add it on, and that completes the square. So half of -2 squared is 1. So we're going to add 1, but if we add 1 here, we got to add 1 over here. So how do you complete the square to get a perfect square trinomial? You take half of that, the linear coefficient, just the y, first power, half of that coefficient and square it and add that on. But if we add it on the left, we have to add it on the right. Now we've got a perfect square. X squared plus y minus 1 quantity squared equals 1. What do we have? Circle, center, 0, 1, radius. This is radius squared, right? Why? Because it's x minus a squared plus y minus b squared equals r squared, where ab is the center, r is the radius. That's our general form. So look at our picture. Circle, center, 1, 0, or 0, 1, radius, radius 1. Let's watch the computer do it nicely, okay? So if I it's not a dance party. In red. Okay, here we go. Let's watch as theta increases. Please work. There we go. That's graphing to sine theta. Center, the red is the computer generated, obviously. Center 0, 1, radius 1, and then the algebra proved what we sketched. Okay, so I'm going to post, there's a little project that you can do, for a parametric project that you can do for some extra credit. Lots of you have been asking for extra credit, so I'll post that. I have your grade. If you want to see your